so let me start.
Can I just quickly thank you? I just quickly want to thank you, Partha. Hi. Thank you very much for doing this. Hi, Dr. Joseph Kirui. Lovely to see you. Everybody else that's here today, thank you very much for being here. I would like to say thank you to Partha Nandi for putting together this whole series of mini school. We've had a lot of wonderful feedback. A lot of people have asked for the mini school link, sorry, the YouTube link, so that they can share this, you know, with other colleagues and students. So thank you very much for that. It's a wonderful body of knowledge that is now archived and put down on our YouTube link channel. So thank you for that. And also I would like to wish Partha Nandi very best wishes for his birthday today.
Thank you.
I wish you have a wonderful day and a wonderful year and another trip around the sun. May you travel safely and may you have many trips around the sun remaining in this life.
Thank you, Miss Rennie.
Thank you very much. Yeah, thank you. Have fun. Yeah. Everybody's going to listen to you. I just wanted to greet and thank you and welcome everybody. Thank you for being here.
Yes. Happy birthday, Professor Nandi.
Yeah, happy birthday. Happy birthday.
Professor Joseph. Okay, so let me start our today's lecture. It is really interesting because today I am going to discuss the quantum fingerprints of gravitational waves through the entanglements. So in our last lecture, we have seen that. So let me please off my camera because it will be easy to, okay, fine. Now, so the point is that in our last series of lecture, we have seen that classical gravitational waves can exhibit entanglement dynamics when the gravitational wave can introduce the interaction between two modes, or it can generate a coupling between two modes of the oscillator detector. So the point is that the gravitational waves can only exhibit the entanglement phenomena if the gravitational waves can couple the individual modes of the detector system at the classical level. And we have also noted that there are two polarization states of the gravitational wave, classical gravitational waves. One is called the plus polarization state, and other is called the cross polarization state. And we have seen that the plus polarization state do not produce any coupling between two modes of the oscillator system. In our case, oscillator system is a two-dimensional oscillator system, which is behaved as an oscillator detector or point particle detector in experience of external oscillator force. Now the point is that cross polarization can generate the coupling between two modes, and this is the key point. And this coupling at the quantum level of the detector will produce the entanglement dynamics. But the question is arise that what about the plus polarization? Plus polarization at the classical level of the gravitational wave do not produce any entanglement phenomena. The point is whether the quantum level of the gravitational waves, or if we are believe gravitational wave can quantize in our future precisions of the gravitational wave detectors, if we increase the precisions of the gravitational wave detector more sharply. So the hope is right that if the gravitational wave has some quantumness, intrinsic quantum nature, then whether this quantumness of gravitational wave can generate entanglement phenomena even if there are no coupling between two modes of the oscillator detector. So the point is that this question the motivated us whether the plus polarization cannot generate entanglement at the level of the classical gravitational wave scenario, but whether the quantumness of gravitational wave can generate the entanglement dynamics corresponding to the plus polarization of the gravitational waves. So let us try to investigate this question. I hope you understand the question. What is our main goal to investigate this lecture? Okay. So now the point is that the quantized gravitational wave in Minkowski space-time, because we have seen that the gravitational wave is nothing but a perturbation or a ripple over flat Minkowski space-time. So therefore, if we believe these perturbations or this effect of gravitations due to the gravitational wave is a so weak effect over the flat Minkowski space-time, then we can express the Einstein-Hilbert action in this following fashion up to a quadratic level of the perturbation. In terms of the perturbation, this perturbation is basically, we have seen that the perturbation is nothing but the fluctuation of the metric with over and above the flat Minkowski space metric. So therefore, this is called the linearization of gravitational theory. And due to linearization, one can rewrite the Einstein-Hilbert action in this particular fashion. And it is a quite well-known expression in the literature. For the reference, those who are interested, really, they can see this book written by the Stefan Weinberg, Gravitation and Cosmology. Now, the point is that this expression, where this h mu nu is the metric perturbation, which already discussed in our last lecture. Now, one can also rewrite this Einstein-Hilbert action at the linearized level in this following fashion. It is a more simple and compact form where this P is a symmetric four-component operators, and these four-component operators, one can immediately notice that these four-component operators is non-invertible operator, because this operator exhibit zero eigenvalue, and due to presence of this zero eigenvalue, one cannot invert this operator. So this is a problem, because this is the consequence. I have already mentioned in our second lecture that if you have some system or a dynamical model which enjoys some gauge symmetry apart from the space-time symmetry, if this system enjoys some gauge symmetry, then you can't find out a unique solution of the gauge field without spoiling the gauge symmetry. So therefore, in order to obtain a unique solution of the metric perturbation through the variation of the Einstein-Hilbert actions, we need to spoil the gauge symmetry. And therefore, we need to find out a suitable gauge fixing condition so that the symmetric differential operator can boils down to an invertible operator. So the point is, the gauge fixing condition is the famous gauge fixing condition, which is known as the transverse stressless gauge condition. And after introducing this gauge fixing condition, one can rewrite the gauge fixed version of Einstein-Hilbert action. To motivate ourselves, I just would like to introduce some steps regarding this statement. The point is that Einstein-Hilbert action, we have seen, it can be written as just up to some constant factor. It is just a d for x, h mu nu, p mu nu rho sigma, h rho sigma. Since mu nu rho sigma is completely symmetric, then and this p is a symmetric differential operator. Now it is a Einstein-Hilbert, it is a completely action for the gravitational field. Now, if we define the total action which incorporate the Einstein-Hilbert action, which describe the dynamics of space-time, plus if we incorporate the matter sector, where this matter sector somehow interact with, so therefore we can introduce the interaction between matter with gravitation. So therefore, let us put some interaction term, matter with the geometry. So which typically looks like this following structure. This part, and we can also incorporate the additional parts, which typically looks like d for x, h mu nu, t mu nu. T mu nu is the energy momentum tensor, which already discussed energy momentum tensor is basically defined as the standard form, which is basically -2 by root g. It is a action due to the matter sector g mu. This is the definition of the Einstein definition of the symmetric energy momentum tensor. So therefore, the total system is basically based on the Einstein-Hilbert action corresponding to the dynamics of space-time, interaction between matter with the geometry, and also one can incorporate the additional part, which is basically, so the total action can be written as Einstein-Hilbert action plus interaction between matter and geometry plus some matter. Matter part is typically, it could be some matter, Lagrangian or action. It could be the fermionic matter, could be the bosonic matter. So therefore, for the time being, it could be a point particle also. We can study the dynamics of a point particle in the curved geometry. So therefore, we know what is the action for the matter, also which incorporate the point particle. So we don't need to write down the explicit form of the matter sector, but the point is that whatever be the form of matter, we can associate some energy momentum tensor. Now, if we study the variation of the total action with respect to the fluctuation of the metric and the stationary condition of the principle of least action at this level will giving rise to the following structure, which is basically this P mu nu rho sigma H rho sigma, which is of the order of up to some constant factor is T mu. So therefore, this is the equation. This is called the Einstein-Hilbert Einstein equations at the linearized level. But in order to solve this H rho, we need to find out the expression of this metric perturbation, because we know that we just introduced the fluctuation of the space-time metric as which deviated from the flat Minkowski space-time matrix. So therefore, this is the expression of H rho sigma, which encode the information of the weak gravitation effect. So now, in order to find out this H rho sigma, we need to multiply both sides by the P inverse. So typically, one can write down this expression in the matrix form as P H times mu nu T mu nu. Now, in order to find out this H, the matrix multiplication, we need to define the P inverse and multiplying from both sides in such a way that it is P inverse H, sorry, it is T inverse acting on T. Now, to define H uniquely, we can write down this P inverse as just identity, which is a replacement of the representation of identity here is a delta Kronecker delta. So one can typically express this H in terms of the P inverse T. So this is a very, 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 very sloppy calculation, because we don't need to follow the explicit steps for this calculation. We need this basic understanding how to obtain this expression for H. Now the point is that if we the moment the P is invertible, then we can obtain the expression of H in terms of P inverse and T. But if this P is non-invertible operator value, the four-component object, then we can't solve this P. It does a unique solution of H. So therefore, in order to obtain the unique solution of H mu nu or metric perturbation, this P must be, this symmetric differential operator must be invertible operator. And if you insist the gauge symmetry is still preserved at the level of Einstein-Hilbert action, then one can show that this symmetric differential operator is not invertible because it can exhibit the zero modes of the eigenvalue. So that is why we need to spoil the gauge symmetry and we need to add some gauge fixing term at the level of Einstein-Hilbert action. And let us define the gauge fixing term as it's called the gauge fixing term, which is basically and define the Einstein-Hilbert action in the gauge fixing way. So gauge fixing term basically kill the term which are responsible for the non-invertibleness of this symmetric differential operator. Now the point is that the moment you gauge fix the Einstein-Hilbert action in a particular way, in our case it is a basically a transverse testless gauge condition. The moment you insist this condition, then we arrive at the following gauge fixed version of the Einstein-Hilbert action. So therefore, this is the expression for the Einstein-Hilbert action at this particular gauge. So now this we immediately observe this is a box operator. It's called the D'Alembertian operator, which is invertible operator. We know that this operator is invertible, and in absence of matter, any distribution in the vacuum, one can obtain the vacuum solution, vacuum equations for the linearized Einstein-Hilbert action is given by this following expression. And this expression, the solution of this equation, this clearly indicates this is nothing but a wave equation. And this wave equation, if we solve this wave equation, we can provide the explicit solution or explicit structure of the gravitational source. The point is that it is a very, very classical expression. And since we know that any wave equation can be expressed, any general solution of the wave equation can be expressed in terms of the Fourier modes. So therefore, from the very fact from the dimensional analysis, one can immediately observe this H should be dimensionless object. Why? Because you know what is the H? H is basically the metric fluctuation. So therefore, we know G mu nu is basically eta mu nu plus H mu nu. Since eta mu nu is a dimensionless object, since it is a basically eta mu nu is nothing but is a diagonal matrix, which is basically +1, -1, -1, -1. So it is a diagonal element. So it is a dimensionless. So therefore, the consistency of the dimension of each term, this H mu nu should be dimensionless object. So therefore, to maintain the dimensional consistency, please wait. To maintain the dimensional consistency, one can introduce the general solution of metric fluctuation at TT transverse testless gauge, which can be expressed in terms of the Fourier modes. Now, one can immediately observe that the summation over K is the momentum modes, and S is nothing but the index associated of the polarization. Since we know that gravitational waves has gravitational field at the linearized level with this particular gauge fixed version enjoy two independent degrees of freedom. And these two independent degrees of freedom we recognize as a two polarization tensor. So therefore, the one is associated to the plus polarization, other is associated with the cross polarization. So therefore, S is associated for the index of the polarization. And this epsilon ij is nothing but the polarization tensor of the each mode. So therefore, this is the very common mode expansion of any field expression at the classical level. So to maintain the dimensional consistency, if we define this Q, I will show you why Q is associated with the dimension of length. If you define the Q in terms of the dimension of length, since the left hand side is dimensionless, exponential factor dimensionless, Lebesgue is also dimensionless. Therefore, we need to introduce some universal constant which has also dimension of length. And we know that the universal constant which enjoy the dimension of length and which encode the information of both gravitation, quantumness, and relativity, which is nothing but the Planck scale. So therefore, we introduce this Planck scale. Why it is universal? Because it is completely independent of the intrinsic properties of any matter. So if one can say that, okay, why not we introduce the quantum scale? But you know, the quantum scale is completely depends on the mass of the particle. So every particle associated with a different quantum scale. So that is why we introduce some universal scale which is valid for for any arbitrary particles. It's not depends on a particular matter or particular system. So that is why we introduce some Planck scale, which expressed in terms of this square root of hg by cq. And you can immediately observe this Planck scale already incorporate the information of three important pillars of theoretical physics. One is gravitation, which is G is a gravitational constant. H bar is a Planck constant, which incorporated the information of quantum mechanics. And C is a footprint of special theory of relativity. So therefore, the relativity, quantum theory, and gravitational effect is incorporated in terms of this fundamental landscape. And S is run from this, as I've already mentioned, is a polarization index. So this is the generic form of the metric perturbation which satisfy the wave equation at the particular gauge. So now the other point is that the polarization tensor also satisfy the following properties. These properties is known as the normalization condition of the polarization tensor. And this properties is known as the transversality condition, and this property is known as tracelessness condition. Since we have already mentioned that the H should satisfy this following condition, this transverse traceless gauge condition, and we try to investigate the solution of H. So this solution must be satisfy this gauge condition, which I've already proposed to the beginning of the wave equations. Now, after imposing these conditions, we can observe that the polarization tensor is already satisfied this following expression. And one can immediately observe that the polarization tensor, the moment the polarization tensor satisfies this following expression, one can introduce this following identity, which is basically which is nothing but a representation of the discrete Kronecker delta. So, why this identity is required? Because the moment we can express the Einstein-Hilbert action at the linearized level in terms of this mode expansion, we can immediately observe the action integral incorporate the four volume. One is associated with the time integral, other is the space volume. So if it's integrated over the spatial sector, incorporating these identities, one can immediately arrive at the following structure of the Einstein-Hilbert action. Now you can immediately recognize this structure. You can immediately recognize the structure of Einstein-Hilbert action. Remind us the structure of the action associated for one-dimensional harmonic oscillator, right? So this is the structure for the action of one-dimensional harmonic oscillator. So therefore, the point is that the moment you rewrite the Einstein-Hilbert action in terms of this following generic expression of H, or in terms of the Fourier mode, the Fourier mode, each mode, the mode amplitude, the Q is the mode amplitude, Q. And one can immediately observe the each mode satisfy the action, or you can visualize the Einstein-Hilbert action is now expressible in terms of the bunch of oscillators where the mode amplitude satisfy the oscillators equation, wherein the omega g is nothing but the frequency of gravitational waves. Now one can identify it. We will identify this omega g is nothing but the energy associated with the quanta of gravitational wave, which will be known as the graviton. So therefore, the point is the moment you re-express the Einstein-Hilbert action in terms of the Fourier mode, each mode satisfies the oscillator nature, oscillator actions. So therefore, the Einstein-Hilbert action is nothing but the bunch of oscillator which is independent oscillators. So one can immediately observe that this L is nothing but is a dimension, it is a length of a box, because we know that when you rewrite the any field in terms of the Fourier mode, you know, the each mode will take the discrete value if we provide the boundary condition. If we provide the finite boundary condition, if we provide the periodic boundary condition within a particular length, it is known as the box normalization. So therefore, the point is that if you provide the box normalization of the Fourier modes, each mode satisfies a box normalization, or if you just consider the gravitational wave within a box with volume V, and this box can be treated as a square cubical box, each length is L. So using this box normalization, one can associate it. This is the length of the artificial box. And this is the universal length, this is the Planck scale. So therefore, this is nothing but the implementation of the Fourier modes of the gravitational field, weak gravitational field. So therefore, it is evident that each mode of the gravitational waves can be treated as a harmonic oscillator with mass m. One can view this expression in front of this time integral just as a mass dimension. So therefore, one can associate it that the gravitational wave can be treated as a bunch of harmonic oscillator with mass m and frequency omega g. This is not a physical one. This is just as a mass dimension. It is an effective realization of the Einstein-Hilbert action in terms of the Fourier. Now, the point is that if we only interested on the plus polarization sector, because we have already mentioned that the plus polarization sector cannot introduce the entanglement phenomena when it interacts with oscillator detector. Only cross polarization introduce the entanglement due to the coupling of the the coupling between the individual mode of the oscillator. So therefore, to identify the sole effect of quantumness of gravitational wave, we will figure out a particular polarization wherein the classical gravitational wave cannot produce any entanglement. So if the gravitational wave can produce the entanglement for plus polarization, this will be the hallmark of quantumness of gravitational wave, because we know classical gravitational wave cannot produce such situation. Okay. Now the point is, we know that for particular plus polarization, if gravitational wave propagate along z direction, the solution of gravitational wave also can be recast in the particular fashion, wherein the sigma 3 is associated with the Pauli third matrix. And we have already observed that in terms of the Fourier mode, the gravitational waves configuration satisfies this following structure. Now, if we only interested a single modes of the gravitational waves, now the gravitational waves visualized is a collection of oscillator mode. And now we are selecting a particular single mode. You can ask the following question: why you are interested of a single mode? To simplify our life. Otherwise, this calculation or situation will be very complicated, because we are just interested to understand what is the essential message can be obtained due to the quantization of gravitational wave. So therefore, to make simplification, we just focus only a single mode of the gravitational field. Now, we know the gravitational wave, when propagate along z direction, the expression of gravitational waves will take this following structure. And on the other side, we know the due to the mode expansion, gravitational wave can also written in this following structure. Now, if you select a particular kth mode, and if one can immediately compare with the expression written in terms of this Pauli matrix with the mode expansion, because both of them is nothing but the different realization of the same gravitational field configuration. So therefore, we can compare them. And after comparison, one can immediately recognize this chi is nothing but chi is just related to this following expression. Okay. And we should remember that this q is now the dimension of length, because one can immediately note that this expression is the action for one-dimensional harmonic oscillator for each mode k. And now the k, this qk is nothing but the displacement of the harmonic oscillator in the momentum space. So now q is the dimension of length. And we know that if you have a harmonic oscillator at the classical level or quantum level, we know how to realize this, the displacement of the harmonic oscillator in terms of the operator version. Since we know if we have quantum one-dimensional harmonic oscillator, suppose p square upon 2m plus half m omega square q square. Q is a displacement. So at the operator level for 1D harmonic oscillator, you know this q can be written as this following expression: twice m omega a plus a diagonal. So this is the quantum version of the displacement of the oscillator, wherein this a and a diagonal known as creation and lowering or raising or creation or annihilation operators. In the quantum mechanics, these are known as lowering and raising operator, but in the particular context in our gravitational theory, we observe that each mode associated with the harmonic oscillator. So therefore, if we quantize, the each modes, so now you can recognize this is the independent set of oscillator. And now pick up a particular kth mode, which is the harmonic oscillator with frequency omega g. Now try to quantize this oscillator. If you quantize each mode, it will effectively provide the quantum nature of entire gravitational configurations. So now, if you the moment you quantize this gravitational the modes of the gravitational field, but particular k, we can express the q at the level of operator in terms of this following structure. Now you can recognize what is the origin of this structure, because we have the harmonic oscillator with mass m with frequency omega g. So therefore, I have already mentioned that this q can be written as in terms of h plus by twice m omega a plus a diagonal. Now, particular case, we introduce new creation and annihilation operator, which is b and b diagonal. Now the question is, what is the meaning of creation and annihilation? It will create something. In the context of quantum field theory, we know that when the B dagger act on some state which is known as vacuum, it will create a particle. And this particle for this particular context known as graviton. So therefore, B and B dagger is nothing but the graviton creation and annihilation operator for the particular mode. So therefore, one can express this Q in terms of this mode creation and annihilation operator in this particular way. And therefore, this chi, this is the classical expression. But if you quantize the gravitational field or gravitational waves in terms of this mode expansion, incorporating this B and B dagger, and if you allow the gravitational wave to propagate along z direction, then this chi also can be recast in this particular structure. So therefore, chi is now the operator valued object. In our earlier expression, we have seen that this chi was the classical time-dependent object. Now this is chi is a operator valued time-dependent object. Why only time-dependent? Because if we consider the gravitational wave propagate along z direction and the oscillator detector placed in the xy plane, perpendicular plane of the gravitational wave propagation, and for the xy plane, we know that the xy plane can be described as a z equal to 0. Okay, so therefore, if we put z equal to 0, then chi will take this following structure in terms of this operator valued expression, wherein B and B dagger create one single graviton with frequency omega g. And now, if we allow these quantum modes, if we allow to interact this quantum mode of the gravitational wave with our quantum detector. Now, the point is that at this level, both of them are quantized. Initially, we have considered the quantum oscillator detector, but still gravitational wave is classical. But now, at this level, we are now considering the gravitational wave is quantized through this mode expansion, and it will interact with the quantum detector, which is one two-dimensional harmonic oscillator. Now, if we allow this interaction for this particular plus polarization, we know for the classical gravitational wave when interact with the quantum detector, we arrive at this following expression. We know this gamma associated with the factor of gravity plus polarization and delta is associated with the factor of cross polarization. But now we are focusing on the plus polarization, so we need to set delta is 0. Okay, because if we allow still delta, then classical gravitational waves also provide some entanglement phenomena due to this coupling, and we don't need this kind of situation because we have already studied what is the feedback of classical gravitational wave on this detector system. Now we are interested to study the effect of only this term, this gamma dependent term. So therefore we just for particular context we just disregarded this term, set delta to be 0. So therefore if you allow the delta to be 0, and if you just focusing on the plus polarized, a particular polarized gravitational wave which is enjoy only plus polarization, then one can immediately observe the classical level there are no entanglement because q1 mode and q2 mode independent mode are completely decoupled. There are no coupling. So therefore this gamma dependent term cannot produce any entanglement because there are no coupling between two terms. But now if we consider gamma is operator valued object through the gravitational wave quantization, okay, still preserving this term is 0, then what would be the physical situation? Now one can immediately observe in the particular setting, if we allow the gravitational wave quantize through the plus polarization, one can immediately observe that the corresponding time evolution operator can be separated out through the time evolution operator of individual oscillator mode of the detector. So therefore, this indicates that initially there are no entanglement through because there are no I need to just clarify the point that this structure indicate that the time evolution operator is act separately the Hilbert space associated of each modes, and this indicate that the plus polarization interaction due to the plus polarization is the local interaction. You see, when you have the classical interaction, so if you just erase this operator value form, and if you just consider the plus polarization dependent term, so one can rewrite this Hamiltonian as two independent Hamiltonian which incorporate the gravitational effect through the plus polarization. So now we know that what is the time evolution operator. Time evolution operator for time independent system is just an integration over I by h bar this h dt prime, and if you allowed some interval, now you can immediately observe that if two operator is completely independent, then this time evolution operator can be written the individual time evolution of independent individual modes. So therefore, this immediately suggests that the gravitational but if we allow this term, you can't factorize this time evolution operator associated of individual mode. If you just consider only the plus polarization, then you can write. This is the consequence of the local interaction. So therefore, gravitational interaction due to the plus polarization is locally interact with the individual. But if you allows the cross polarization, it will couple to individual mode through the following interaction, and this indicate that the q1 mode interact with the momentum of p2. So therefore it will generate some non-local interaction at the quantum, non-local operation at the quantum level. Okay, relativistically all of them are local, but at the operator level they will be treated as a non-local operator. Okay, now the point is, if you just consider the class polarization now, the time evolution operator can factorize in this manner. So this is the indication of the system locality So this was not satisfied for our classical calculations or classical situation. So therefore, this is the important message. So local interaction, local operator, local operation. So this is known as a local operation cannot generate entanglement. Local, the point is that local, in other words, local classical operation, because this gamma is now the, if you consider gamma is the classical gravitational field interaction, they cannot generate the entanglement, because we have already seen this situation only happen if the cross polarization will be taken for the particular Hamiltonian. So therefore, the question is whether the local quantum operation can generate entanglement. The meaning of this statement is, if you further quantize this gamma dependent coupling or through the operator value nature, because we know that the gamma depends on, what is the expression of gamma? Gamma depends on chi dot, and if you consider chi is an operator valued object, then this is still local, but point is the local operation enjoys the quantum background interaction. Now, the point is that whether this local operation through the quantum background interaction can provide entanglement between two subsystems. In order to investigate this question, let us first put down the operator valued notion of gamma in the following structure. Because gamma is related to the chi dot, so after first order time derivative, you can achieve this following structure where C depends on this following expression, and which represent the constant term. And now let us consider the initial state. Let us consider, since we are considering some interacting system where the quantum gravitational field, because we are insisting only the single mode. So therefore, this is the expression of gamma associated of the single quantum mode of the gravitational wave. So now, when you consider the single mode of the gravitational wave, which is quantized, and the time evolution operator now incorporate the quantumness of both, quantumness of detector, quantumness of the gravitational sector. So therefore, when this time evolution operator act on some initial state, this initial state should be written in this following fashion, where the first part of the initial state is just a ground state of the detector, harmonic oscillator detector, which, well, since it's a two-dimensional detector, so therefore we just consider the both oscillator mode situated in the ground state. And the second sector through the tensor product, the second sector associated of the vacuum of the gravitational field. So therefore, the vacuum means initially there are no graviton. So therefore, this is the situation when you have no graviton. So this is known as the vacuum. The concept of vacuum can only realize if you quantize the field. So this is the very common concept of the quantum field theory. And now, if you try to evolve this initial state, which incorporates, so therefore the this initial state incorporate the notion of both quantum notion of, so these provide the quantum notion of detector, oscillator detector, and the last sector is associated of the quantum notion of gravity. So the gravitational theory we incorporated in terms of this following state, in quantum gravitational theory in terms of linearized level, incorporated this in terms of this following initial state. So now if you try to evolve this initial state incorporating this following expression, we arrive at some final state at time t in interaction picture. Now the point is that one can immediately calculate the density matrix through this final time evolved state. The density matrix is nothing but the outer product of Kate and Brass state at time t. So therefore, this density matrix now incorporate the information of both quantumness of detector, quantumness of gravity through the graviton. But still, when you just focusing on the detector sector, and we are trying to investigate what is the quantum fingerprints of the quantumness of gravitational wave, we just want to try to measure this quantum fingerprint through the indirect evidence. So therefore, we are not directly measure the graviton. So that is why we just tracing over the gravitational sector. So therefore, first initially we tracing over the gravitational sector. Through this indicate that we trace over the all possible graviton states through the final state, because the final density matrix incorporate the notion of gravitons and excited mode of the detectors. So therefore, we just try to focus on the particular quantum modes of the detector when it interact with the quantum modes of the graviton or gravitational waves. So therefore, initially we first trace over the gravitational part through the integrate or tracing over the graviton sector. Then we tracing over the second degrees of freedom of the detector, because we are just considering a two-dimensional detector which has 2 degrees of freedom or 2 modes, and we are just focusing on the particular modes. We are just try to focusing on the particular modes in a such a way that we just tracing over the other modes of the detector and tracing over the gravitational modes, which is incorporating the graviton states. Now, after tracing out this following sector, we arrive at a reduced density matrix. And if you calculate again the entanglement, von Neumann entanglement using this reduced density matrix, one can immediately observe that the reduced density matrix will take this following structure after the using up if you just considering the relevant approximate term which associated with the linearization of initial gravitational field. So therefore, this non-trivial component of this entanglement entropy can be rewrite in terms of this K2. Why this 2 has important meaning? This K2 can be expressed in terms of the time integral of this object. Now, this object is purely quantum object. There are no classical counterpart of this object. This object is nothing but 2-point correlation of the vacuum. So therefore, it's nothing but the vacuum fluctuation of the 2-point correlation, or sometimes it is known as the Green functions. So therefore, this non-trivial correlation function of gravitational waves encode the quantumness of the gravitational field. So therefore, since we consider the initial gravitational field in suppose have some quantum fingerprint through the quantized mode, that is why we finally arrive at this following structure. And this is purely a quantum object because the classical gravitational field or gravitational wave cannot produce such expression, such non-trivial expression. And after calculation of this simple time integral, one can arrive at this compact form of this K2. So this suggests that the classical gravitational wave cannot create some entanglement, but still the quantized or quantum mode of single mode of quantum gravitational waves can create a non-trivial entanglement dynamics between 2 independent modes of the oscillator. So therefore, this is the hallmark of quantumness of the gravitational field or gravitational wave, because the classical gravitational wave cannot exhibit such phenomenon. So therefore, let me finish by conclusion. This is the final conclusion. The classical gravitational wave cannot generate the quantum communication through the entanglement between 2 disjoint systems. And the quantum gravitational waves. So therefore, the quantum gravitational wave with plus polarization. We know that with plus polarization, the interaction term has a local form, and we know that the classical local interaction cannot produce entanglement. So this is known as the famous statement that LOCC, local operation classical communication, LOCC, local operation classical communication cannot exhibit entanglement, right? Because we have already observed this situation. If you insert only the gravitational waves for this plus polarization is gamma is a classical parameter, there are no entanglement because there are no coupling. So therefore, this is a still local operation, but background is classical. So the classical local operation cannot generate entanglement. But if you allow this gamma is quantized, so this is the quantum local interaction. So therefore, the point is the quantum local interaction, the gravitational wave can generate entanglement through the two-point correlation of the gravitational waves. So the local operation and classical communication, the entanglement between two distant objects is impossible. But in our case, the local operation is not augmented by the classical communication, because the two individual mode of the oscillator now communicate through the graviton, and graviton is the not a local not a classical communication, it is a quantum communication. So therefore, the two independent modes can still entangle if they incorporate or they interact with the quantum modes of the gravitational field. So this is so therefore one can immediately understood that the entanglement feature through the quantum mass of gravitational wave is the key observation of quantum theory of gravitational waves. So I think we can stop here. Are there any questions? Hello, can you hear me?
Yes, sir. I would like to ask a question. It is not a question, but I have some doubts. Like you said that the gravitational waves can be treated a bunch of SHO as a bunch of SHO when it is quantized. And now we want to communicate between the two different modes of this SHO via graviton, and this is considered to be the entanglement states, right?
So therefore, so first of all, you should clarify yourself. There are three mode interaction. The first mode associated with the detector oscillator. Okay. And now detector oscillator interact with the quantum mode of the gravitational wave, which is the another oscillator. So there are three oscillator modes. Do you follow?
Yes, there are three oscillator modes.
Three oscillator mode. One oscillator mode is associated with gravitational sector. Other two oscillator mode is associated with the gravitational wave detector, which is advanced LIGO detector.
But here the question is that the entanglement process is an instantaneous process. So the graviton will travel to modes via greater than c velocity. This part I am having a little bit of confusion. Or the interactive fields. For that reason, they can have.
Not the entanglement. This is not the instantaneous process, because to avoid the instantaneous process, we just introduce the concept of field. You know that it is not the action at a distance situation. Right? Because the graviton propagate, if it is a massless particle, it is just a propagate at the velocity of c. So, but now the question is that two independent mode can entanglement through the correlation between the graviton sector at the two-point level, two-point correlation. So this is not the instantaneous. You can immediately observe that why it is not instantaneous, because it will associate it with two different time. You see?
Yes.
So therefore, there are time interval t1 minus t2.
Two different time scales.
Right. Anything else? Any other questions? Okay, so if you have no more questions, then I can stop here.
Yes.
Yes.
Dr. Nandi, so what are the major problems of detecting gravitons?
Oh, no. The point is that we are interested to see the quantum effect of gravitational waves, not one interested to detect the graviton. You see, the gravitational wave detection is so sophisticated scheme. We are not directly try to detect the gravitational theory. I mean, the gravitational theory detected through some indirect process. So therefore, we are interested to see the effect of gravitational, the quantum effect of gravitational wave through some indirect effect, because the direct detection of graviton is not it is not direct process, because it is a very complicated process, because the gravitons is a massless theory in a particular context, and we are just interested to ask the following question: whether the gravitational wave detection can provide a justification of quantumness of gravitational waves. Do you follow? It is our motivation. I'm not saying sorry, say again.
Okay, yeah, I see.
We just try to provide some justification whether the gravitational wave detection can we provide a justification of quantumness of gravitational theory through the gravitational wave detection, because we can't detect the gravitational theory directly because it is a very, very weak effect.
Okay, yeah, that's true.
Okay.
Yeah.
Okay, so